Today we get to test the claim about the mean when we know the population standard deviation. So last time we tested the claim about a proportion. Remember how to do that because that's going to still continue to follow us along. But now we're going to be testing the claim about the mean when we know the population standard deviation. So this section presents methods for testing a claim about a population mean given that the population standard deviation is a known value. The population standard deviation sigma is known in this section. That is going to be a key thing to pay attention to as you do your homework and to remember when we get to the end of things and we're putting it all together of pay attention to whether you know the standard deviation of the population or only the sample standard deviation. And I know that's one of those things that caught a few of you on the last test, on Chapter 7's test, was not reading those closely. You got used to just doing this section and then this section and then this section and not paying attention to what's the difference between each of these different sections in the chapter. And so this one you have to know sigma, not S. You still know S. Obviously, if you've created your own sample, you may know the sample standard deviation, but if you know the population standard deviation, then you're going to use that instead because that's for the entire population, not just your sample, especially if you're trying to find information about the entire population. So our notation, N is still our sample size, X bar is still the sample mean, mu sub X bar is the population mean of all sample means from samples of size N. When you're testing a hypothesis, we assume we know the null hypothesis to be true, so that value would be the number we're going to use for mu sub X bar. Now remember when we were doing things, I don't remember which chapter it was even in, if it was chapter 6 or 5, when we were using that central limit theorem, that the mean of the sample means is the population mean. Well, that's what this is coming from. This is the mean of the sample means. And so the mean of the sample means would become the population mean. If I took every population of that same size and took every single combination of those samples of the same size N, and took the mean of the sample means, it would become the exact same value as the population mean. And so that's that theory behind where we're pulling this information from, is that central limit theorem. Also, the standard deviation has to be known, so sigma is the known value of your population standard deviation. Well, when we talked about the central limit theorem, we had these requirements, and so these still are showing up. The requirements for testing claims about a population mean. When you know the population standard deviation, the sample has to be a simple random sample. That is almost a blanket statement for almost anything you're doing in statistics if you have to have a good simple random sample first. The value of the population standard deviation, sigma, is known. And either or both of these conditions are satisfied. Either the population is normally distributed or the sample size is greater than 30. And those were the things that came from that central limit theorem, that if you already had a normal distribution, then the mean of the sample means would already be the population mean. On the other hand, if your sample size was bigger than 30, then when you're taking those means of your sample means, then they're going to tend towards your population mean immediately anyhow, without having to take every single sample of that same size. You're going to be able to get towards that population mean anyhow. It's going to give you a nice normal distribution. So, test statistics for testing a claim about a mean. So if we were to rearrange one of the equations we had from Chapter 7, so back on Chapter 7, when we were finding the margin of error, when we knew the population standard deviation, I guess let me zoom a little closer. Well, the margin of error is that difference between my population mean and my sample mean. We ended up using that test statistic of z sub alpha over 2. Well, if I solve it for z, then I would multiply both sides by the square root of n, and I would divide by sigma. Well, notice we're taking the margin of error, and we're dividing by, I guess it just divided by the square root of the sigma over the square root of n. Is doing that same thing. So it's just rearranging that same equation that we just had and solving it for our z. So this gives me my test statistic. That's the part that's coming from my sample values of what I'm going to use. You're still going to need to find your critical values or your p-value and determine whether my test statistic is in that critical region, if you're doing it the traditional method, or find what your p-value is for your test statistic to determine whether or not it's going to be a p-value more or less than your alpha, your significance level. All right, so let's do an example. Do a number 14 on page 431. So it's following in this one I want to do the traditional method, so we're going to do it by hand first. It's still going to follow the exact same steps that we followed before, which I don't remember what page number that was on. The one's on page 406. So following that exact same pattern that we were doing before. So if we look at number 14, the weights of bears. The health of the bear population in Yellowstone National Park is monitored by periodic measurements taken from anesthetized bears. A sample of 54 bears has a mean weight of 182.9 pounds. Assuming that the population standard deviation is known to be 121.8 pounds, use a 0.05 significance level to test the claim that the population mean of all such bear weights is greater than 150 pounds. So first of all, what is my claim? Okay, my claim is that the mean is greater than 150 pounds. If my claim is false, what's going to be true? Okay, my mean will be less than or equal to the 150 pounds. And putting down that what that false is not necessarily something you have to write down, but at least think about is a good choice as you're doing these. So what is my null hypothesis? Okay, my mean equals the 150. Which means my alternative hypothesis is which one of these two. So which one does not include the equals? Okay, that first one, that the mean is greater than the 150. Now, as you write down these, make sure you're putting the mu in there, that you're talking about it being the mean. Don't just put down equal 150 and greater than 150. I want to know what I'm testing, and this time I'm testing the mean. And knowing that I'm testing the mean directs me into what type of test statistic I'm going to use. If I didn't know I was working with mean, then I don't know if I'm using proportions or standard deviation or what I'm working with. Okay, next thing we need to do, now that we have our null hypothesis and our alternative, we are going to be testing the null. We're going to assume that it's equal to. Based off that assumption, how likely is it that I would get this sample data coming out of things? So the next thing I need to do is to find my test statistic. I need to find my z. So you're going to take your mean minus, this is what we're going to get from our null hypothesis. This is what we assume to be true of the population parameter over the population standard deviation divided by the square root of n. Oops, went the wrong way. And so for our example, my sample mean was the 182.9. Mu is the 150, because that's coming from my null hypothesis. I'm assuming that to be true. Population standard deviation was given to us as 121.8. And we had a sample size of 54. So go ahead and find z using those. Should be getting 1.98. if I'm doing the traditional method, first of all, what was alpha in this problem? Okay. And knowing that significance level is something we had to have before we start doing the test and the whole entire problem anyhow. So now, if I'm doing this with the traditional method, is this a left-tailed, a right-tailed, or a two-tailed test? Okay, right, because the alternative is that it's greater than. And so if I'm doing a right-tailed test, that tells me I want all 0.05 to be in this right tail. So what is that critical value that gives me all 5% in the right tail? So using your Z tables, because we're looking at a Z test statistic. So if I'm wanting 5% in the right tail, I'm looking for the 0.95 in the body of my thing. No, it's not 1.96. Okay, so my critical value is the 1.645. Because that gives me all 5% in the right tail. The 1.96 gives me it in the two tails. So since this is just a right tail, the whole 5% is in the right side, so I want the 95% in the left. Now, the question is, where does my test statistic land? So my test statistic is 1.98. 1.98 is past 1.645. So is that in the rejection or the fail to reject region? That is in the reject region. So this is going to reject the null hypothesis. So from what I'm doing, I am rejecting that I know the true mean to be 150 pounds. Now we have to go back and make our statement based off what the claim was, not just from the null hypothesis. My claim was that the mean was greater than 150 pounds. So when I go to try to figure out my wording, did my claim include equals? Okay, since I just claimed that it was greater than 150 pounds, it did not include the equals. Did I reject or fail to reject? We rejected. So the sample data supports the claim that the mean weight of bears in Yellowstone National Park is greater than 150 pounds. So this is one of the only times that we get to support what we were claiming to be true, is when we did not include the equals to begin with and we were able to reject that null hypothesis that it did equal. So the sample data supports the claim that the mean weight of bears in Yellowstone National Park is greater than 150 pounds. Questions there? Because this shaded blue region it's only going to happen less than 5% of the time that my true mean is 150 pounds and I get a sample that's this extreme. So since I got the sample that was that extreme, I'm going to assume that my original assumption that the mean equaled that was false. So if you're out here in these extremes, which in this case, if it's past my critical values, my rejection region, then I reject that null hypothesis. If I'm in this place where it's close enough that it might have just happened by chance, that's in that fail to reject your null hypothesis. Because now it's close enough that it may actually be 150, and I can't say that that was wrong if it's in this non-shaded region. Okay, other questions? Now, this was doing it by the traditional method. If we did the p-value method, so down here we got z to be 1.98. We said our null hypothesis was that the mean was greater than 150. I'm sorry, that's not the null, it's the alternative. The mean equaled 150. My alternative was that the mean was greater than 150. We got z to be 1.98, and we knew alpha to be 0.05. So bringing over the most important stuff out of the previous problem. If I'm doing the p-value method by hand instead of doing the traditional method, the p-value method is saying what is the probability that I can get this test statistic to be this extreme or more extreme given that the true mean is 150 pounds. So I take my test statistic, which is my 1.98. Because this is a right-tailed test, then I'm going to find the probability that it's that extreme or more extreme. And remember, this p-value table is right above our wording of the conclusion, where it walks me through how to find my p-value, where I'm asking, is it a left-tailed, a right-tailed, or a two-tailed test? Because I'm doing a right-tailed test, it's greater than, my p-value is just the area to the right of my test statistic. If it was a two-tailed test, I would have to take the area and double that. But because it's just a one-tailed test, I'm just finding the area that extreme or more extreme. So using my tables, what do we get for the probability that we're at 1.98? Actually, what is the area to the left of 1.98? Let's ask that question first. Guys, are you checking your table? So finding the probability that it's to the left of 1.98. Are we all getting 0.9761? Okay, so once I know that 0.9761 is my area to the left, my area to the right is 1 minus 0.9761, which is what? That is the probability. That is my p-value in this case, because it's just a right-tailed test. It is that area there. So my p-value is the 0.0239. I compare that probability compared to my alpha, my significance level that I'm allowing. If I want alpha to be 0.05, is that higher or lower than 0.05? Lower, so is that a reject or a fail to reject? That is a reject. So I'm going to reject the null hypothesis. I will come to the same conclusion whether I use the traditional method or the p-value method. It's just the path you're taking to get there will look different. Questions on that? Now we're back to our wording again. Our original claim did not include equal. Since the claim did not include equals and we are rejecting the null hypothesis, then the sample data supports the claim that the mean weight of the bears is greater than 150 pounds. So it's the same final wording on our conclusion will be the same. And notice when I go back, I'm going back and restating in simple words what the original claim was. And it's not that it supports the claim that whatever, or supports that so-and-so believes this to be true. It's supporting the claim that it truly is greater than 150 pounds. Questions on that one? Now the piece that you guys all want to know, how do I let the calculator do it? The calculator is able to do the p-value method. You're going to go under statistics, arrow over to test. This time it is a z-test because you're using your z-score to test a hypothesis. You know the statistics. You don't have the original data. You had the statistics of knowing the population mean, and when you have sigma in there, that tells you it's from the population, and that should be a warning bell right there of double checking yourself. Did this really give me the information about the population, or did I only know the information about the sample standard deviation? Determining whether I'm going to get to use the z-test or whatever we'll talk about next time. Probably, I don't know. Yeah, something was wrong. It's probably because we didn't have the stat plot on. But I'm not 100% sure because I've never tried to do that. Yours, Drew? Also, it gives you what the thing looks like as far as what part's shaded in. So when she had things on there, it drew it to look like this. Okay. So as you're doing this one, it's going to tell you your z-score, that'd be in the 1.98, giving you your test statistic. And then it gives you your p-value being the 0.0239. Questions on that? Yeah. Was yours off a little bit? 3.6, okay. I'm kind of surprised it's off that far, but I'm not. Yeah. Because I would have thought the tables would have had that one closer, since 1.98 was something we actually was able to see on the table. Although, did we round? We rounded that z-score to 1.98, didn't we? When we did our test statistic back here, when we did this, we rounded that to 1.98, so that's where we rounded at. That's what caused the rounding error. Because a z is not exactly 1.98, your calculators are telling you exactly what it is. And so, since we rounded that and then used the tables, yes, there's a rounding error. On the test, p-values, since the tables give you to 4 decimals, just keep your 4 decimals. Your z-scores are to 2 decimals, wherever that was, 2 decimals, so just keep 2 decimals. When you even if you take it from the calculator, just go ahead and keep the 2 and the 4. I will have it both on the test if I'm doing it by hand and if I'm doing it with the calculator. Even for the p-value, I'll have my answer written over here by hand. And then the calculator, actually I'll probably have the calculators first, but then I would also have the calculators being the 0.0236. And both of them are good. So yeah, both of them are good. Okay, other questions on that? So trying to figure out what the reasoning is behind what's going on. If the sample results or more extreme results can easily occur when the assumption that null hypothesis is true, we attribute the relatively small discrepancy between the assumption and the sample results to chance. So when we get something, if I have said that the mean was the 150, which is when I'm going to get my z-score to be 0, and if I end up getting something that says, okay, so I went out and I weighed these bears and they turned out to be 155 pounds instead of 150 pounds. Well, if you went through and found the z-score for 150 pounds or 155 pounds, it's going to be close. You're probably looking at a z-score of like 0.2 or something like that. It's going to be a little bit above it, but not a lot. That happens by random chance. Just because the true mean of the entire population is 150 and you go out and you weigh some bears and you get them a little heavy, that can just happen by random chance. Even if I got out to being this was 182, so even if I got out to being 170 pounds, the 170 pounds is probably going to land right about here. Again, being a little heavy will happen by random chance. You might have picked 1 or 2 of the heaviest bears in your sample of whatever that sample size was in this problem, of 54 bears, and so that kind of skewed my data a little bit. But this is trying to say that if I was going out and just randomly picking bears and my weight of my mean was this 182.9, that my sample was that much heavier than what the true mean was, that's probably not going to happen by random chance. It's only going to happen by random chance less than 2.5% of the time. Very unlikely that I'm going to go out and pick this really heavy sample by just random chance. Still could, and that's that alpha is that type 1 error, that I might actually be rejecting the null hypothesis when I shouldn't be. But I'm going to make that assumption that it's not probably going to happen by random chance. It's probably my original assumption was just wrong. And that's what we're using on this, that if the sample results cannot easily occur when that assumption is true, so if I'm assuming I know the null hypothesis was that the mean really did equal 150, but that's such a small chance that it's only going to happen less than 2.5% of the time, if that assumption doesn't easily happen, we explain the relatively large discrepancy between the assumption and the sample results by concluding that the assumption's not true. So we have to reject that assumption. We're assuming that we know the null hypothesis. It doesn't happen very likely that that null hypothesis is true and my sample is right at the same time. So one of those things has to be wrong. And so since I made an assumption about my null hypothesis, that's probably the piece that's wrong. Oh, I want to do another problem before I let you guys go. Let's come back to this one. Let's look at number 18. So at number 18, dealing with garbage, the totals of the individual weights of garbage discarded by 62 households in 1 week have a mean of 27.443 pounds. Assume that the standard deviation of the weights is 12.458 pounds. Use a 0.05 significance level to test the claim that the population of households has a mean less than 30 pounds, which is the maximum amount that can be handled by the current waste removal system. Is there any cause for concern? Number 18. So first question, before we can even start plugging it into our calculator, is does it meet my requirements? Did I come from a simple random sample? We're assuming that to be true. Yeah, there's something else before that. Oh, do I know the population standard deviation? And is my sample size normal or greater than 30? So since it's greater than 30, I don't care if it was normal or not. Okay, so I get to use this process. So go ahead and use your calculators and put in what you know. Okay, so in this problem, most of you didn't write it down, but what was our null hypothesis? Okay, we were assuming that the population, or the population mean of the garbage was 30 pounds. What was our alternative hypothesis? Okay, that it was going to be less than 30, because that was what we were claiming, is that the mean weight is less than 30 pounds. So then when you went in and did your calculations with the calculator, what did you get for Z? Should be a negative 1.62. Okay. And then what is our p-value? So now the question is that a reject or is that a fail to reject? If alpha is 5%, isn't it, in this problem? Alpha significance level is 0.05. So since it's over 5%, that is a fail to reject. Oops, I forgot an E on there. Because if the null is low, or sorry, if the P is low, the null must go. If the P is high, the null will fly. So this is you're failing to reject that null hypothesis. Now, if you follow along and figure out what our word is in this problem then, did my original claim include equals? Okay, we were just claiming that the mean was less than 30 pounds. So it did not include it. We failed to reject it, so we're on this very bottom one. There is not sufficient sample evidence to support the claim that the mean weight of the garbage is less than 30 pounds. Now, figuring out what kind of conclusion that means, if there's not sufficient sample evidence to support the claim that the mean weight of garbage is less than 30 pounds, and they're saying in the problem that which is the 30 pounds is the maximum that can be handled by the current waste removal system, do we have a problem? Sounds like we have a potential problem that people are throwing away more garbage than what the system is ready to handle, and so they need to be looking at that. Because it may be potentially that we're having things overworked and having significant problems. All right. Let's see, today is Wednesday. Friday. Oh, shoot, I forgot about getting all that organized for you guys. Friday, I'm not going to be here. And I was planning on doing Section 5 on Friday. You guys, your class is the class I keep forgetting that I'm not going to be here Friday on. I know. I think I'll make a integrity video for you guys tomorrow. Okay, let me ask this question. Would you rather have me not have anything Friday and lose one of our days for the review for the final? I think I have like 3 days of review for you guys. So would you be okay just being down to 2 days for reviewing for the final? Okay, so I'm going to let you guys vote since I'm really hearing one person with a strong opinion. So let's go this way. Thumbs up is no class Friday. Thumbs down is that you want class Friday. So no class Friday, which means you lose a review day. Thumbs down is class on Friday, so you can keep 3 days of review. Well, okay, integrity class on Friday or no integrity class on Friday? Yes. Thumbs up for going and doing class on Friday. I have a majority is with the thumbs up. So no class Friday, losing a final review day. So no class at all Friday, nothing to watch, nothing to do.